It's just setting up the recording now. Okay, so what's today's date? Today is Friday, March 27th. This is our Friday Zoom meeting, and we're just going to do a couple of quick things in this video. One is I just want to share out some positive information. Some of that information is that 70% of students turned in this week's quiz, which is pretty cool, and over 95% of students did the Khan Academy lessons. So I think that's pretty good news. I'm going to share my screen so you can see some things that I want to bring to your attention. There are some things that I'm a little bit worried about. One of them is if you're looking at my YouTube screen here. Emily, I'm going to go ahead and unmute you, but you got make sure that there's like not a lot of background noise, okay?
Okay.
So if you're looking at my screen, you'll notice that, see where my mouse is hovering? This video here, this video here, and this video here. These three videos here are the videos that I posted for this week, and they have pretty low views. So the most number of views anything got was 42 views, and given the number of students I have 111 students.
Yeah, not all of them watched it.
Exactly. So that's something that is of concern to me because, and I want to say this as clearly as I can, if in your different classes, not just math, but if in your different classes, your mentality is that you're only going to do the things that have to be turned in, then I think you're going to be in some trouble. And so what I mean by that is this. Let me go to this week's kind of table of assignments. So I think that there's this danger that people are only paying attention to the highlighted items, the stuff that has to be turned in. But I want to give you an example of the kinds of stuff that I'm not collecting this, but this is where you're actually learning the math. So for instance, here I am, I'm looking at the date for, I don't know, Thursday, March 26th, and there's this hyperlink for these problems that I want you to try out. When I click on it, it opens up a PDF, and this PDF has these problems, these simplifying radical problems. And just like I would do in class, I'm saying, listen, the idea is to try them out. Just give them a shot, see where you go. You take ownership of the content. And then once you've done everything you think you can do, and you're like, okay, so what are the answers here? I've provided not only the solutions, but my work, the worked out solution, so to speak. So I guess one of the things as a teacher I'm a little bit worried about is, are students doing this kind of stuff? And I'm asking it rhetorically. I have no idea. On top of it, the YouTube channel I was showing was referring to places like this where I've embedded videos for you to watch. So I just wanted to put that out there that if you really want, like during this time, hopefully we're not just focused on grades, we're also focused on, we can't get this time back. We want to learn this content. You're only going to be a sophomore or junior once, hopefully. So why not get the content while it's available? Other thing I want to mention is that I will always try to post the following week's lessons over the weekend. So either tomorrow or Sunday, I'll be posting next week's whole week's lessons, everything like the problems you want to solve, the videos you want to watch, all the resources, so that you can budget your time the way you see fit. We have 3 assignments next week. We have a chapter test that you're going to submit with Google Forms. We have a website, New York Times, what's going on with this graph, that you're going to visit, study a graph, and you're going to post your responses as comments. And I also have a set of Khan Academy assignments. So all that is already ready. I'm just waiting for the weekend to post it. Okay, let's go over the quiz that was due today. How's that sound, Emily? Is that cool?
Yeah.
Okay, let's do it. So here's the quiz. It's going to stay online. I've still made it available. And even though I'm not technically accepting anymore, I wrote on that site that if you had some extenuating circumstances that were beyond your control, just shoot me an email and we'll work something out. So I'm now going to toggle to my document camera so you can start seeing solutions for 1A through D. So let's do that. And M, since it's just just you right now, I want to ask you, let's see how well this is showing up. Is it pretty legible?
Yeah.
So I'm going to walk through these because it's a video format. So if anyone ever needs to go back, they can. Problem number one, the idea is to find out where the function begins, and the strategy is to take the radicand, that word ends in the letter D, and to ask for what values is this radicand defined. So you'll notice that I'm setting that 4x plus 3 greater than or equal to 0. When I solve, I find that as long as x is greater than or equal to negative 3/4, then this radical function is defined. What's happening when x is equal to negative 3/4? This radicand is equal to 0. And the root of 0 is 0. When you add on a 2, you get the number 2. So the graph begins at negative 3/4, comma 2.
So you have to plug in like the 3/4 back in.
That's exactly right. Or
Oh, I didn't do that as well.
yeah, or you can remember that the question really is, so where did this negative 3/4 come from, right? It came from asking when the radicand was equal to 0. So you already know what's going to happen when you plug in the negative 3/4. You're going to get 0 under the radical sign. The square root of 0 continues to be 0. Making it negative doesn't change it. The only value that's left here to attend to is the number 2. So that's why you get negative 3/4, comma 2. As far as question B is concerned, which asks what quadrants does it show up in, you know, I don't know what people are doing because we're not in class. It's not the kind of test where I can say don't use a calculator. I encourage people not to use one on this problem. What I did was I listed out the transformations in order, the order in which they happen, and that taught me that the function shows up in quadrants 1, 2, and 4. Shows up in 3 out of 4 quadrants. Question 1C is based on what you get for question 1A. If the function begins with an output of 2, and ultimately it kind of, this is a pretty horrible sketch, but it goes through quadrant 2, a little bit of 1, and into 4, then the outputs are just getting smaller and smaller. So the largest output is 2, and then all the other values are less than 2. So we write that the range is y is less than or equal to 2. And then I think I'd asked, what's the third transformation that the function undergoes? And that's just order of operations. So the 4 is the first value that causes a transformation, then followed by the 3. Some people think that the square root sign is something that's causing a transformation. It's not. That's just the argument of the function. The third thing that happens is you're taking the negative outcome of this radicand. And so what that causes is a reflection over the x-axis. So that's question number 1. Let's talk about question number 2, which simply says, compare these two functions. The classmate's having difficulty understanding them. Use complete sentences to describe or explain how these functions are in fact different. And so actually, I don't know that I even need to really toggle back to that other screen. Clearly, there's notational differences. The negative signs are in different places, and the number 3 or the numbers 3 are in different places. So the question is, what does that cause? And the answer is, for function A, that negative sign causes a reflection over the y-axis, and then that 3 causes a translation to the right. I'll show you a sketch of that in a minute. But in this problem, because of the order of operations being different, this negative sign now causes a reflection over the x-axis, and this 3 causes a translation up 3 units. So a kind of a rough sketch of that looks like this. Function A looks like this. You can see the reflection over the y-axis, translation to the right. Here, the function has been reflected over the x-axis, and it's been translated up. So
for A, can you hear me?
Yeah, I can
For
hear
A, if it's 3 units to the right, why is it going like left?
Say that one more time, Em. You're asking why it's going to
Oh,
the
I think it's because of the reflection, right?
exactly. You
Oh.
kind of answered your own question. If it was just x plus 3, then yes, it would have gone to the left. But because it's negative x plus 3, it ends up moving to the right. Okay.
Okay. Mm-hmm.
Let's go to number 3, where the classmate decides to consider this equation. This is one of the videos I'd created that did not get a ton of views. even though like I did a screen recording of how to use Desmos to problem solve. In any event, the idea is, will these two meet in space? And the answer is, yep, absolutely. They meet at the ordered pair 3, comma 3. So you would just enter these equations separately into a graphing calculator or a graphing utility, which is just a fancy way of saying some kind of software. And you'd find that the solution's at 3, comma 3, first quadrant. And then I'm following up to 3 by saying, okay, now solve it algebraically. And when you do solve it algebraically, some pretty funky stuff happens. And I want to know what's happening. So I'll show you what's happening now. So here I am. Let me just adjust my camera. Here I am trying to solve that same equation algebraically. I'm squaring the equation, and I find that x is equal to -1 or 3. So I'm kind of puzzled. I'm like, wait a minute. When I graphed it, I didn't get 2 answers. I just found that x has to be 3. And this is where you have to check those answers. When you plug in the -1, the outcome you get is that the root of 1 is equal to -1, which is not true. This -1 ends up being what we call an extraneous solution. The number 3 continues to work. So that's what I was looking for in 3B, for people to understand that when you're solving these equations algebraically, oftentimes the algebra produces answers that are not accurate. That takes us to number 4, where I asked, is either of the following equations true? And this kind of problem is detailed in the textbook and the readings that I assigned and some of the problems I did, some of the examples I did. Equation A is the distractor. It's absolutely not true. It is not true that you're taking each of these values and raising it to the second power. I can't emphasize enough that that's not true. What's actually happening is that equation B is true, and here's why. I'll show you under my camera why that's the case. So bear with me as I'm moving the stuff around. This is what's happening. You're actually taking that binomial and you're multiplying it by itself. So the same way you would always multiply a binomial, you'd multiply the first 2 terms, the outer terms, the inner terms, and the last terms. So 2 things times 2 things gives you 4 different things. The 2 terms in the middle, they don't cancel each other, but they're like terms. So equation B is the true equation. How you doing, Emily? Are you hanging in there?
Yeah.
Awesome.
It's hard to solve those though.
It is. Well, think about it this way: you're not solving them. You're changing their representation. You're changing the way they look. So I
No,
agree.
but like with regular like multiplying binomials, it's way easier. That one is like confusing
It
because
is. Yeah.
there's
I
numbers before the radicand, so I don't know like what are like terms because they look like they go together, but at the same time they look like they go separately.
yeah.
I don't know.
Actually, that's an awesome question. Thank you for asking that. So I can clarify. Ready? So here I have 5x minus 2, don't I?
Yeah,
And here I just have the lonely number 9, right?
yeah. I know where you get the 9 from, but
Yeah. So but the question you asked was about like, how do you find these like terms? And I guess the way I see it is, I'm going to write on the side of my paper, like if I said to you, what's 3x plus the number 5 plus the number 3x, right? Whoops, it's getting cut off. Your brain has trained itself to recognize that this 3x and this 3x are like terms, right?
yeah,
In the same way, think about what you have here. You have -3 of what? Of this thing that we're calling the root of 5x minus 2. And then you've got another -3 of what? Of that same thing, the root of 5x minus 2. So you end up with how many of these things? -3 minus 3 is a total of -6
6.
of these root of 5x minus 2. So the radicand is like that x in that previous problem. You just have to learn to recognize that that makes them like terms.
So for the you see where you multiply the root of 5x minus 2?
Yep,
They just cancel each other out and the radicand goes away.
that's
Like,
exactly right. That's right.
yeah,
When you multiply a radical by itself, that radical sign goes away. It's like multiplying the root of 3 times the root of 3. If I did root 3 times root 3, you'd actually be ending up with the root of 9, wouldn't you? But that's just known as
yeah,
number 3.
3. Okay.
So in the same way, multiplying a radical expression by itself removes the radical sign, unless, like in this case, there's some stuff outside of the radical sign. Okay?
Mm-hmm.
Let's take a look at question 5 and 6. I don't know that I'm going to do a lot of narration here, but I do want to share my work. And again, if anyone watches this recording, then they can. And by the way, I hope this recording works. I know it's recording, but I don't know how tough it is to share it. So that's something I'm going to be learning about. But anyway, let me show you my work for 5 and 6, okay?
Mhm.
So let's start with 5. It's quite a bit of math, so I guess I should just do it in parts. And if you'll allow me a second to find all this. So let me just say some highlights about strategy here. 5a has 2 radicals, and so I don't want to square it right off the bat. I want to separate the radicals onto different sides of the equation, and then I want to go ahead and square. You'll notice that the left side just turns into 3x plus 1. But the right side is just like the previous problem. It's taking the root of x plus 4 plus 1 and multiplying it by itself. So you still have a radical there in the mix, which means we're not done. I continue to collect like terms until by this step here. Can you see my mouse hovering over the work?
Yeah.
All right, cool. By this point, I have just the root of x plus 4, and over here I've got x minus 2, and you'll notice, what am I doing again?
Squaring it to
Squaring
get
again.
rid of it.
And that's where I became suspicious that people weren't watching videos or doing practice problems, because that's one of the major themes that I highlighted, that you often have to square more than once or raise to some power more than once. So what happens is you get a quadratic. It seems like you have 2 answers of 0 and 5, but you're always checking those answers. And so when you do, you realize, listen, 5 works, but 0 ends up being extraneous. And that's what you see above is my actually taking the 5 and the 0 and plugging into the original equation to see if it's valid or not. I chose 5b because it had a different kind of radical situation. This time, to get rid of the 1/3, you actually had to raise to the 3rd power. And doing so produces this answer of x equals negative 42.
Do
And
you always do that when it's fractions? You do like the reciprocal of it?
yes, I wouldn't call it the reciprocal, though. I would call it the inverse.
Mm.
What we're saying is that the opposite. Well, let me use a simple example. If I say to you x plus 5 is equal to something, the inverse of that is to say, well, you were adding 5, so I'm going to go ahead and subtract 5. Here,
Mhm.
when you're raising something to the 1/3 power, the opposite of doing that is raising that value to the 3rd power. So I would call it the inverse operation. So yes, if something is being raised to the 1/3, the inverse is always to raise it to the 3rd. If something is being raised to the 2/3, the inverse is raising it to the 3/2, and so
Mhm.
on. So yeah, when you do that, you end up with this outcome of x equals negative 42. And then 6 was critical because I think a lot of students didn't realize that when you're solving radical inequalities, it's a 2-step process. So let me use, it's just bringing everything into focus. Let me use 6a as an example. You'll see that I wrote first and second. What I'm
Yeah.
saying is, first you have to just investigate that radicand. You have to ask, for what values is this radicand defined? And it's only defined when x is greater than or equal to negative 1. Then you solve the inequality algebraically, and it gives you an answer of x is greater than or equal to 7. And then this is the part where it's a thinking exercise, because you're like, wait a minute, here I am on a number line, and I want my answers to be greater than negative 1, but I also want them to be greater than 7. Well, if I choose a number in this region right here, it satisfies the requirement that it's bigger than negative 1, but what does it not satisfy?
Greater than -7.
Greater than 7, exactly.
Okay, so 7.
So that's all right. My writing's not the best. So then logically, you have to say to yourself, okay, well, I'm trying to report answers that work all the time. And the answers that work all the time are the values that are greater than or equal to the number 7. So that's it. That's the true answer. And it covers all the numbers that are greater than negative 1, essentially. And the same thing happens in 6b, where again, you have to look just at the radicand. When is 4x minus 4 greater than or equal to 0? When x is greater than or equal to 1. And then you solve this inequality algebraically, and you find that x is less than 10. So I always use a number line because it helps me visualize these answers. I'm like, oh, okay, my numbers have to be greater than or equal to 1, but less than the number 10. So the answer
I
ends up
got
being,
that right. I just made a mistake when solving it. I had the 1, but like I put 8 instead of 10.
got it. So just like a computational error, right?
Yeah.
Cool. And what time is it? I want to make sure I'm not cut off by Zoom.
11, 12.
Say it again.
11, 12. I mean
Cool.
10, 12.
Cool. So we're doing okay. Um, do you mind if I share? Sorry, I'm like juggling all my screens here. Do you mind if I share uh, the Khan Academy? People did, I think I said at the outset of this video that people did a really nice job on Khan Academy, except for the very last lesson, which was on these extraneous solutions. So, do you mind if I work through two problems that might help folks? Is that cool? What do you think, Em? Is that all right? Let's see. So, actually, let me start with the Khan Academy. So,